This question is exactly the same as those in the previous skill, except this time we also have to draw the Lewis diagrams ourselves. So, in this question we have a scientist trying to predict the enthalpy change of reaction for the reaction between carbon monoxide and oxygen. Our first step is balancing the equation. Again, I'm not going to show how to do that here. If you need more practice on that, go back to Unit 14. To balance this equation, these are our coefficients we're going to need, 2, 1, and 2. Our next step is going to be drawing the Lewis structure for each compound. Then we're going to use those Lewis structures to calculate the total bond energy for each substance. So let's go ahead and draw our Lewis structures. I'm going to start by heading to my periodic table to find out how many valence electrons carbon and oxygen each have. Here's carbon. Carbon is in group 14, and here's oxygen. Oxygen is in group 16. Being in group 14 means carbon has 4 valence electrons. Being in group 16 means oxygen has 6 valence electrons. Okay, so we're going to start our Lewis diagrams by drawing a single bond between each of our atoms. So we'll have a single bond here, a single bond here, a single bond here, and a single bond here. Our next step is to add our remaining electrons for each atom onto our diagram. So carbon has 4 valence electrons. Right now there's 1 used up in that bond, so we're going to have 3 more electrons shown on here. 1, 2, 3. Oxygen has 6 valence electrons. 1's been used up in the bond, so we've got 5 more electrons to draw on here. So 1, 2, 3, 4, 5. Okay, we can do the same thing over here. Oxygen has 1 electron used up in this bond, so 6 in total, which means we've got 5 left to add on each of our atoms. 2, 3, 4, 5. 1, 2, 3, 4, 5. And then the same down here, we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then 1, 2. For our carbon, since carbon has 4 valence electrons and 2 of them are being used up in the 2 bonds that it's making, so it has 2 left. Okay, so now we've got all our electrons on our diagram. If we have any single electrons on their own, those can be made into bonds. So this single electron and this single electron together are going to be made into a bond here. We'll do the same thing here. This single electron and this single electron can be made into a bond here. This single electron and this single electron can be made into a bond here. And this single electron and this single electron can be made into a bond here. Our next step is to check if the octet rule is being followed for each of our atoms. So in the carbon dioxide down here, oxygen has 2 pairs of non-bond electrons and 2 bonds, each providing 2 bonding electrons. So that's a total of 8 electrons. So oxygen there is good. Carbon has 4 bonds, which means 4 sets of 2 bonding electrons, which is a total of 8. So carbon's good. And then the oxygen over here again has 2 lone pairs, so 2 sets of 2 non-bonding electrons and 2 bonds, which is 2 sets of 2 bonding electrons. That's a total of 8 electrons. So carbon dioxide is all set. What about our oxygen? Here we've got 2 lone pairs, so 2 sets of 2 non-bonding electrons, and 2 bonds, so 2 sets of 2 bonding electrons on each of our oxygens, which gives us a total of 8 for each. What about on our carbon monoxide here? So for the oxygen, we've got 2 bonds, so 2 sets of 2 bonding electrons, plus 2 lone pairs, 2 sets of 2 non-bonding electrons. That's a total of 8. So that's good. For carbon, we've got 2 bonds, so 2 sets of bonding electrons, plus 1 lone pair, 1 set of 2 non-bonding electrons. That's only 6 electrons there. So the carbon is our only atom that doesn't meet the octet rule. What we can do is take one of the pairs from the oxygen atom and form that into an extra bond here. And let's recalculate to make sure that the octet rule is met for both of those atoms. For the oxygen, we've got 3 bonds providing 3 sets of 2 bonding electrons and 1 lone pair providing 1 set of 2 non-bonding electrons. That's a total of 8. And for the carbon, again, we have 3 bonds and 1 lone pair. That's a total of 8 electrons. So our Lewis diagrams are all done because all of our atoms are now obeying the octet rule. So now we can go ahead and calculate the total bond energy for each of our compounds. For carbon monoxide, we have 1 triple carbon-oxygen bond. So looking down in our table down here, here's our triple carbon-oxygen bond. It has a bond energy of 1072 kilojoules per mole. So our total bond energy for carbon monoxide is 1072. What about for oxygen? This time we have 1 double oxygen-oxygen bond. Let's find that in our table. Here's our double oxygen-oxygen bond. It has a bond energy of 495 kilojoules per mole. So our total bond energy for oxygen is just going to be 495. Lastly, for carbon dioxide, we've got 2 double carbon-oxygen bonds. Let's find that in the table. There it is. Our carbon-oxygen double bond is 799 kilojoules per mole. So our total bond energy is going to be 2 times 799, which gets us 1,598 kilojoules per mole. So we can go ahead and fill that in an answer box here. Awesome. Okay, so we know the total bond energy for each of our compounds. Next, we're going to calculate the enthalpy change when the bonds of the reactants are broken. Now remember, breaking bonds is endothermic. It takes in energy to break bonds. So this is going to be a positive number. And to get it, we're going to multiply the total bond energy of each compound in a reactants by the coefficient in the reactants and add them together. So we've got 2 sets of carbon monoxide. Carbon monoxide has a total bond energy of 1072 kilojoules per mole. We're going to add 1 set of oxygen, which has a total bond energy of 495. So if we calculate that out, that's going to get us a total bond energy for our reactants of 2,639. And it's positive because we're breaking bonds, which takes in energy. It's endothermic. Next, we're calculating the enthalpy change when all the bonds of the products are made. Now, making bonds, that is exothermic. So that releases energy. So this is going to be negative. We have 2 sets of carbon dioxide. Carbon dioxide has a total bond energy of 1,598. We put that on our calculator. We're going to get a total bond energy for the products of negative 3,196. And the negative sign is because the bonds are being made, which is exothermic. It releases energy. So negative 3,196. Awesome. Okay, so we've got our energy that's absorbed when the bonds of the reactants are broken. We've got our energy that's released when the bonds of the products are made. All we need to do is add those together to get the total energy change for this reaction. So it's going to be 2,639 plus negative 3,196. That's going to get us an overall enthalpy change of reaction of negative 557 kilojoules per mole. Lastly, is this endothermic or exothermic? Since we have a negative sign, we're releasing energy. Overall, this is an exothermic reaction. That means that the energy needed to make the bonds in the products is greater than the energy that was needed to break the bonds in the reactants. So in this question, again, it's just like the previous one. Firstly, we had to go through and figure out the Lewis diagrams for each of our compounds. Then we calculated the total bond energy for each compound using the table. Using our balanced chemical equation, we then added up the energies of our reactants and products to find the enthalpy change when those bonds of the reactants are broken, that's endothermic, which is positive, and when the bonds of the products are made, that's exothermic, which is negative. Finally, we add those together to get the enthalpy change of the reaction.